Thank you. So, thanks for having me. Hi, everyone. I'm Benoît. I'm working as a freelance software developer, contributing to different libraries in the Python scientific ecosystem, more or less geospatial. I'm also a Xarray developer. And yeah, before moving on, I should mention that what I'm presenting here is not my own personal work, but it is the result of a joint effort with all these people shown in the slide involved. It's a result from a code sprint that we had a few months ago. And also I should mention that it is very, like what I'm going to show you here is very preliminary results. So apologize, there's no like a full feature library that you can install and use right away. But hopefully I'm going to show you that this is something that has that can be useful and that has certain potential. So the talk is focused about data cubes. So I guess that most of you are familiar with the concept of data cube. For those who are not, this is how it looks like. So it's a cube with some data in it, basically. In the case of geospatial data cubes, you have like 2 dimensions for space, and then you can have an additional dimension. Could be time, could be vertical layers, or whatever. They can be more dimensions, or beyond 3D. And also, very often, we have different variables or data fields packed into the same data structure, like shown here, like this 9 subset boxes with different variables. So a few examples, like this one is ERA 5 reanalysis weather climate data. It's a global data cube, so it's in latitude, longitude coordinates and full extent, full coverage. Which, well, we can use it just right away. There are some applications where we want to do global analysis or doing slides in a cube without really caring about the coordinate reference system. So that's fine. But for more advanced application, probably like extracting zonal statistics and so on, then we might get into a little bit more trouble, I would say, where we need to project the data and so on. Another example is satellite imagery, so a stack of rasters with additional dimensions like time and spectral bands. Here, this is Sentinel-2 data. It's projected data on UTM zones. And yeah, so as you can see, there is a curse of dimensionality in data cubes. So even with like 2 additional dimensions in addition to space, then the data set can become pretty big, like almost 50 gigabytes in this case. So if so it's for a limited extent in this case. If you want to increase the coverage, then you might get also into trouble. So how, like which coordinate system to use for projecting data. Like, yeah, there are different options that you can do also for dealing with large amount of data, like tiles or building pyramids and like aggregating data on coarser resolutions and so on. But still, some troubles regarding projections and so on. So one question arises, isn't it a better way to represent this kind of gridded data sets or data cubes on the sphere? And one answer could be this thing called Discrete Global Grid System, or we call DGGS. So what it is, basically it's a tessellation or partitioning of the entire Earth's surface, most often approximated as a sphere, and is partitioned evenly into a hierarchy of grid cells or grid zones. System H3, I think that's the most popular one, or at least that is the one that I've seen the most often in presentations in this conference. And this is maybe because it's a well-maintained library coming from Uber that has been well advertised. And I also heard in another presentation this morning that, yeah, hexagons are very appealing shapes. But yeah, that's one grid system, but there are actually a variety of other grid systems. There is a few of them here. On the top left, this is the S2 geometry from Google, which is pretty popular too, but maybe more used behind the hood in applications. On the top right, this is HEALPix, which comes from the domain of cosmology, astrophysics, but there are also other applications in earth science. And then the two at the bottom is, other kinds of grid systems. And yeah, as you can see, one grid system can vary quite much from another one. It depends on various properties, like obvious one is the shape of the cells. Here it can go from triangles to quad cells to hexagons. Also, it varies depending on the distribution, how the cells are distributed on the sphere, what we call the aperture, so how the cells are subdivided from one hierarchical level to another. Whether also between two adjacent hierarchical levels, whether the boundaries of the cells exactly match or not. For example, you can see in HEALPix or S2 that, so here I forgot to mention that there's two different levels that are shown here, like the bold lines is one parent and here the more thinner lines is just the level below the bold lines. Yeah, and you can see in HEALPix S2 it overlaps or the boundary match, but not exactly in H3. So yeah, there is a variety of DGGS cells. There's no like a perfect global grid system that suits perfectly every kind of application, but it's rather depending on the application. You might want to choose a system over another. For example, if the local representation of the neighborhood is important, then maybe using hexagons will be a good choice over, for example, using HEALPix or S2 with diagonals. But for other applications, HEALPix might be a good choice. For example, HEALPix has this interesting property that all the cells have roughly the same, cover the same area, which is not the case of other grid systems. So yeah, many different global systems for different applications. But all these systems have some properties in common. They all provide a hierarchical structure. So it's very friendly for multi-resolution data. As you can see in the animation here, this is on the HEALPix grid, and this is output from climate models and going on a finer and finer resolution. And also all global grid systems provide a unique indexing system, which is very useful for spatial indexing, building spatial indexes. And it is also worth mentioning that there is an OGC working group working on standard for DGGS. Okay, brief overview of the existing tools and libraries for working with DGGS. So yeah, there's quite a few of them here in this mentioned in this table. As you can see, most of them use compiled low-level language for implementation for performance reasons. Some of the libraries are specific for one global grid system, while others, like DGGRID, it implements a variety of grid systems, or even grid system that you can build on the fly using a few parameters. And yeah, what about DGGS in landscape in Python? So yeah, most of the core libraries here also provide some Python bindings. This is the case of H3 Pi, which is bindings of H3 or S2, which also provide kind of official bindings. There are also, besides that, other libraries built on top of the core libraries and providing more high-level features. And yeah, not all these libraries are equal in the sense that some of those libraries are still actively maintained, some unfortunately aren't anymore. Also in terms of performance, they are not on par. So if I take the examples of H3 Pi, for example, it provides binding for certain function. It works with NumPy arrays. So you can do a lot of operation in compiled code, and it's pretty fast. But it's only for a limited set of functions. So other functions, we need to loop over the cells or features in pure Python, which is pretty slow. That's also the case of S2 Sphere, for example, typo here, which is a pure Python implementation of S2. So not great for performance there. And yeah, all these libraries have also their own specific API. So for example, if you want to work with DGGS in Python and say, I'd like to compare between different grids and see what is the best for my application, then I need to go over all these libraries and then learn the API and learn the specifics of each of them and so on. And while all provide the same kind of features. Right, so it might be tedious, it adds a little bit of friction, and yeah, the ecosystem is a little bit fragmented, I would say. Can we do something? Yeah, probably. What about like working towards a unified API in Python that would make things easier? That would be nice. And yeah, we think a good starting point is Xarray. Here again, I assume that most of you already know Xarray, just core library in Python for working with data cubes, often seen as labeled NumPy arrays or multi-dimensional panda data frames, even though it goes beyond that nowadays. And yeah, this figure there illustrates the Xarray data model with a bunch of variables on 1, 2D and beyond dimensions, all gathered into a fancy containers like data array and data sets. And one thing interesting is something that has been added recently in Xarray is custom and flexible indexes. So historically and still today, when you create a new data set or data array, for the coordinates where the name matches the dimension, there is a panda index that is built automatically from the coordinate data, which is very useful, which is very handy for selecting data on the data array or data set based on the coordinate labels. It works well with a lot of applications, but sometimes for certain applications might be limited. And especially in this case, if you look a little bit more closely to the values of the county coordinate here, it's not like primitive integer or float values. It's what we have here is shapely objects, shapely geometries, which makes it a little bit limited with panda index, because panda index doesn't have the capabilities of doing, for example, spatial selection, spatial queries, and so on. But no, we can, instead of panda index, provide some custom indexes. And this example is actually taken from the XFEC package, which is an Xarray extension for working with vector data cube. And one thing specific of XVec, it's providing a Xarray custom index, a geometry index that works with shapely geometries. You can see it here. It's also aware of the coordinate reference system. So what we do here, dropping the panda index and replacing by a geometry index from XVec. And then the great advantage with this is that we can then reuse the Xarray API, like from the Xarray core library, to do more advanced data selection, here based on shapely bounding box, for example, with different predicate methods. And then what we get is this spatial aware data selection, and also nicely with the county coordinates with a geometry index that has been propagated from the original data array to the result data array. So yeah, that's a nice feature. I should say that Xarray custom indexes, this is a feature that is still kind of work in progress, so it's not, there's not yet full support across Xarray, but it works today, so it's used actually in XVec. It hasn't been well advertised, but hopefully things are going to be better very soon. And I should also mention that in the case of the geometry index here in XVec, it's still applied to one-dimensional coordinates, but with Xarray custom indexes, you can create index for any arbitrary set of coordinates of any arbitrary set of dimensions, which makes it very flexible and powerful. Then back to global grid system. There is Xdggs, which is part of this talk. And yeah, the idea with Xdggs is leverage these Xarray custom indexes the same way as it is used in XVec, like vector data cubes. So very like basic example here, using H3, loading a netcdf file with some data on H3 cells. So where we have here is a cell coordinate with so some integers here. So this is one thing specific to DGGS. So those global grid systems usually encode every cell as a unique, using a unique identifier, which most often is an integer, but sometimes it might be something else. So here, yeah, I have data on a cell dimension with represent H3 cells, but it still has this panda index. But with using Xdggs, the idea is to have now a DGGS aware index. So yeah, let's go to a demo. Maybe I should also, yeah, make it a little bit bigger. Okay, I just showed you the code snippet examples using H3, but the idea is to also make Xdggs work with other kinds of global grid systems or other backends, like here in this demo using HEALPix. So currently there's H3 and HEALPix that we support, but in the future we plan to add so other systems. So again, here loading some netcdf file with some coordinate with a bunch of cell ideas, and it doesn't have any index, panda index, because it's not a dimension coordinate, but yeah, we can assign a DGGS index from the cell IDs coordinates, and now we have a HEALPix index. And it knows what kind of global grid is because of those attributes attached to the coordinates, so HEALPix with some parameters that are specific to the HEALPix grid system. So now we have a specific index that we can do that also manually, like this, specifying explicitly the HEALPix index class, but it's the same. And then now we're ready to perform some data selection, like for Panda index, regular Panda index. We could do some selection using cell IDs, but yeah, it might be useful for some application, but yeah, using cell IDs directly is not very user-friendly. But fortunately, can also select some data using latitude and longitude values. For example, here, just one longitude value and two different latitudes, so it's point-wise selection. So I select, in this case, two different cells. And in the result, you can see still the HEALPix index here. Other interesting things, like extracting cell boundaries and assigned the extracted cell boundaries into a new coordinate called geometry, in this case, and the resulting data set has a new coordinate with shapely objects. Yeah. And this is where it gets also interesting, because it shows you the interoperability between X-ray, different X-ray extensions. So it means that we can reuse now XVEC and set an index for this new geometry coordinate. So we have a data set where we can do either data selection using the DGGS index, or like perhaps consider each cell as an arbitrary polygon and then do some more operation, because not all spatial indexing operations are available in DGGS systems. So for example, use selection using cell geometries, using XVEC, like providing a bounding box, and it works, and it also selects the cell ID, so we still have this HEALPix index around in the result, so if we want to switch back to do something with DGGS. And because XVEC is also integrated with GeoPandas, we can convert that into a GeoPanda data frame, and then reuse all the capabilities of GeoPandas, for example, for plotting the data and showing the data, as you can see here. So this is the HEALPix cells that we can see here. All right, so that's it for the demo. That's a short demo, and there's not much features I've been showing you, because there's not much more feature right now in Xdggs. But yeah, the plan is to add much more features, and yeah, first of all, maybe having some convenient methods for converting data from and to DGGS, because otherwise it's pretty much useless. So converting from regular latitude-longitude grid, for example, converting from raster, or from point data, because the global grid like H3 are also used quite much for aggregating point data. So that might be useful. And also conversion methods and the other way around. As I showed you, extracting cell geometries for using with other packages in a geospatial ecosystem, like cell boundaries, but we can have also envelopes, or like rectangular bounding boxes, or cell centroids could be useful too. More advanced spatial queries, when a global grid system supports it, then it would be nice to have this feature available from Xdggs for working with X-ray objects. But it's probably not always the case, so alternatively we still have the way to and the choice to convert cells to arbitrary vector geometries and use tools like Xvec. Doing also hierarchical operations might be useful to change from one resolution to another. For example, something that looks very much like what's available in X-ray, the reindex method, or using some aggregation, reusing X-ray API like group by. Data cube alignment, so working with data cubes on the same grid system or on different grid system, and compare those data cubes or align it, at least check which global grid system is used, and throw an error if it's not like the cell IDs are on different systems. And finally, plotting. So I've just shown you the demo like that we can convert into a vector data and then reuse all the tools available for plotting vector data. But what we can do also is convert to a gridded or raster, and then or gridded latitude longitude grid, and then reuse other tools. Or perhaps interesting in the case of H3 or S2, if you've seen Kai's Baum presentation yesterday about Lawnboard, is that it's using DGGL in the front end, and DGGL has support for plotting H3 and S2 cells, which means that we would only need to transfer cell IDs over the network to show. So it might be a good option and really fast and efficient. So yeah, I'd like to finish this talk showing a little bit of landscape of geospatial tools that are gravitating around X-ray. So I think with this DGGS we really have something for all the kinds of data representation, geospatial data representation. So we have for raster, RIO X-ray, vector Xvec, and then in between, triangular networks, there is another extension called U-X-ray for unstructured mesh. And then there is this Xdggs. So if everything interpolates well between each other, then it means that we can use Xarray as a tool to go from one representation to another pretty easily. With because I think also like this different the boundaries between these representations are overlapping to each other. So it's nice to go from one presentation to another. Yeah, and that's it. Thank you. So there's the code repository here. Please feel free to contribute. It's a community-led initiative, so contributors are welcome. And yeah, you can find me on this link. And thank you.
Thank you, Benoît, for the interesting talk. Are there any questions? We have time for maybe one or two questions.
Thank you for a very interesting presentation. I was wondering, you're using now global grids. I myself am using a local grid only for Belgium with the local projection. Would it be also feasible to integrate that into Xdggs?
So you mean with a local projection and complex cell shapes?
It's just squares, but it's just the extent is limited. It's not global. it's local. Let's say in my case, it's only Belgium,
Mhm.
or or a bit wider, but
Yeah.
not global.
Yeah, so you could also work on limited extent. So yeah, put it back to this example. All we have in the cell coordinate here is a bunch of cell numbers. So it doesn't have to cover the whole Earth surface. It can cover only a limited extent, or it can even be sparse. So you have different cells sparsely distributed on a region of interest. So if your data covers limited extent, you might be able to, if you want to, map it to a global system, but with a limited extent.
And what about adding a new index type? You support H3, S2, maybe some others. Is it easy to create a custom index type?
Yeah, so we want to design this for easily add new backends. Yeah, because it's changing rapidly, like the backend libraries with new libraries for this kind of grid. So yeah, we want to be flexible in adding new kind of grids. Yeah.
Okay, thanks.
Okay, thanks again, Benoît.
Thank you.